this computer. Yes. So please, Teresa, floor is yours. Thank you.
Okay. Thank you very much. First of all, thank you very much, María Jesús, for the invitation and for the opportunity. Really, I have heard a lot about this lecture series, so it is really an honor to have the chance to participate. And thank you everyone that is attending, because I know this is almost the last day before Christmas, so this is much appreciated. So today, like María Jesús just said, I'm going to talk about a topic we've been working on for the past couple of years, which is how can we use additive manufacturing to improve the efficiency of electric motors. As you can see, there is a long list of authors here. So this is a collaborative effort, and I'll introduce them to you later a little bit in a couple of slides. But I want you to first take a look at this part that I have here in the cover, because this is the focus of this talk. So we are going to focus on a specific component of the electric motor, which is the rotor. This is a moving part. And as you can see, it has quite complex geometry. So this is going to add another layer of complexity, to the work we are going to try to do. But let us start from the beginning. Let me see if I can pass the slide here. Yes. So what is the motivation for this work? And I want to go with you through this estimation of the energy losses in electric motors in Europe. Because the first time I saw these numbers, I was really very, very surprised. So in Europe, we have about 8 billion electric motors, and this is including transport, including industry, and so on. And they consume about 50% of all the EU electricity production. So this is a huge number that you can see here, 1,350 terawatts per hour. This is a huge number. Let us estimate the losses. So we have, of course, many different types of electric motors. Some are very efficient, so the losses are smaller than maybe 1-2%. Other motors, they lose 25% of the energy. So let's assume we take a bit of an optimistic average, which is 5%. So if we calculate that, the amount of energy that is generated, that then is transported, distributed to each of these motors, and that is wasted, is about 30% of all the electricity consumption in a country like Spain. So these numbers are really huge. And I think there is a lot that we can do here. And this was the framework that motivated us to work on this topic, to try to contribute here. And this is aligned to the mandates of COP28, where they suggested we need to double energy efficiency by about 2030. So there is a lot, like I said, that we can do here. Let us see a bit more concretely what are the sources of energy losses in electric motors, because there's many types of energy losses. And here I have just a cartoon motor that I took from the internet, but we're going to focus, like I said before, in this part here. This is the rotor. This moves under the influence of dynamic magnetic fields that are generated here in the stator, and it's mostly made by silicon steel. So there's many sources of losses, but the three that I want to highlight today, the three that are more relevant to this presentation, are these ones here. So the first one is eddy currents, so the heating of components. How could we mitigate eddy currents? Well, if we could replace silicon steel by another material that has a higher electrical resistivity, that could be one way. Then there is another source of losses, which are magnetic type losses. So this is because, of course, silicon steel is a soft magnetic material, but it's not a perfect soft magnetic material. So we still need some energy to magnetize and demagnetize the material. And how could we mitigate the second source of losses? Well, if we could replace the steel, but another material that is even softer, that has a smaller coercive field. We are going to see that in more detail later. And then there is a third source of losses that are related to motor design. So with the current manufacturing methods that are more widely available, we are limited in terms of geometry, and we cannot manufacture the complex geometries that would be ideal to guide these changing magnetic fields. So if we could get a manufacturing method that would allow us, would enable more freedom of design, we could also mitigate this type of losses. So let's see what can we do about that. What we propose in the project that I'm going to introduce you in a minute is to see and to explore whether we could substitute this silicon steel by iron-based metallic glasses, which are also soft magnetic. And these metallic glasses the peculiarity, that they have if they have an amorphous structure. So, and this disordered structure conveys some properties that are very extraordinary. Let me talk about that in more detail. Now we are going to talk about iron-based wool metallic glasses, because we have many families of wool metallic glasses. And just a small parenthesis, because before I start talking about the properties, I'm going to talk about some magnetic properties, but I'm going to focus only in one of them more mainly. Here we have a hysteresis law. So here we have in the vertical axis the magnetization of the material, in the horizontal axis H, this is the applied magnetic field. And the property I'm going to focus on in this is this HC, which is the field we need to apply in order to magnetize the material. So of course, for a soft magnetic material, we want HC to be as small as possible. And let us then review what are the coercive fields, the coercivities of different families of alloys. So here we have in this domain the silicon steels. And here, in this orange domain, we have iron-based metallic glasses. As you see, there is a wide dispersion because, of course, we have many different types of alloys within, iron-based metallic glasses. But there is high potential also in some alloys for some compositions to have a very, very low coercive field, and thus to reduce these magnetic losses. But not only that. So these materials, if we are able to stabilize them in a fully amorphous form, they have high electrical resistivity. This is three times larger than silicon steel, and they have extraordinary hardness. So structural function is not the main function here, but of course we always want robust components, so they have high hardness. So what is the problem then? If we have such good properties, how come we are not using these materials? And the reason for this is that there are very high technological barriers to produce bulk, especially complex geometry components with these materials, because in order to stabilize this amorphous phase, which is what conveys them these nice properties, we need to use very fast cooling rates. Here you have the range between 10 to the 4, 10 to the 6 Kelvin per second. And of course, for most manufacturing methods that we have available, this is not possible. So there is only a few manufacturing methods that can do that. And the most commonly used here is melt spinning. This problem is particularly pronounced for the alloys that have low, what we call glass forminability, which means that even if we cool the liquid, the liquid metal very, very fast within that range, there is a maximum thickness that we can make in amorphous form. And you'll see that for the materials that are of interest for this talk, the glass forminability is only between 100, 150 microns. So this is very, very small, and almost the only method that we can use to produce these materials in amorphous form is by melt spinning. So here we have a container. The shaded area here is the liquid metal, and we apply a gas pressure here. So we shoot the metal towards this rotating copper wheel, and in contact with the wheel, it cools down very fast. And we have, as a result, these ribbons, which are, maybe like 100, 150, 200 microns. So these are fully amorphous, but of course, there is not much we can do with them, and they find only very niche applications. So this is the reason why, despite the good properties, we can really not make bulk components. So a window of opportunity opened when additive manufacturing techniques became more widely available a few years already ago. And the technique I'm going to focus on in this talk is laser powder bed fusion. For sure, many of you have know already how it works, but I'm going to highlight here two important characteristics of this technology that are very, very relevant for what we are talking today. One is that, well, as you know, this is a layer by layer process. As the laser melts, this specific powder layer, it cools down, the material locally cools down very fast at rates that are between 10 to the 5, 10 to the 8 Kelvin per second. So covering the range of cooling rates that we need to stabilize the amorphous phase in these metallic glasses that we are studying today. And then, so this is one thing. We could in situ potentially make these amorphous materials. And then the second feature that is very useful for us is this freedom of design. We said that a third source of losses was related to the design of the component, the impossibility to make these complex geometries. So in theory, with additive manufacturing, laser powder diffusion in this case, we could simultaneously and potentially make this fully amorphous component with a complex geometry. So suddenly there was a window of hope, but of course things are a bit more complicated. And for these materials that we are interested in with such a small glass forminability, it is difficult because there is mostly crystallization during processing, and it is complicated to stabilize the fully amorphous form. So this is back in 2022. We were searching for a breakthrough. When I say we are, it's an entire consortium that I'll introduce you in a minute. But we wanted to do this, to make a bulk, complex shape component, fully amorphous, fully dense, and also with an iron-based metallic glass with a very specific composition. So with no phosphorus, because this is very volatile, with no cobalt, because of the large societal impact of cobalt, and with no rare earths, because of the problems in supply chain and so on. And these alloys, like I was mentioning before, the glass forminability is close to 100 microns. So this was a big challenge, and we applied for funding for a Pathfinder Open project that we got already started in March 1st, 2022. For 4 years. So we are about to finish in February. Actually, this project is done. So I can tell you now, I promise you I'm going to give you some good news, but I will also tell you about all the challenges that we face to solve this problem. And this is the consortium. The consortium is coordinated by Professor Ralph Busch in University of Saarland, Isabella Galino, that then moved to TU Berlin. They are experts in glass science. So because this was a complex challenge, we are tackling it from different directions. So one is alloy development, and this was the task of Saarland University. Then we partner with Macemet, with our experts in powder atomization, and both us at IMDEA Materials, in parallel with Amloy in Germany, we were working in process optimization. So this talk today is going to be more focused on process optimization, how far we have gone. And in particular, LPBF, that's the process we work with. And we partner as well with the group of Paola Tiberto in INRIM in Italy, who are experts in magnetism, magnetic property measurements, and so on. So let's see. We started from the beginning. So at the beginning, there were very few, it was very difficult we didn't have, of course, time to design the alloys. This is day one. So we had to start, in order to learn how to optimize the process, we had to start with whatever was commercially available. And it was very difficult to source these materials in powder form because, of course, the glass formulability is so small. We can basically only make ribbons. So there was not many suppliers that were ready to give us that. But we found a Japanese company, Admix, and they could provide us with two alloys that are the ones I'm going to show right now, Cuamet and Finemet, and I'll show you later the composition. So we thought, let us start understanding well the fundamentals, what are the relationship between the LPBF processing parameters, the structures of the printed parts, and the properties. And we start with a simple scanning strategy, just to understand the basics. And by simple, I mean this meander scanning strategy. So just back and forth with the laser, and let's see how far we can go with this strategy and with the commercial alloys. So we worked in parallel with this alloy Cuamet. You can see the composition here, iron, silicon, chromium, boron, carbon, and Finemet. Most of the slides of the results I'm going to show you are related to Cuamet because actually they behave very, very similarly. I'll show just some scattered slides about Finemet, but basically the storyline is the same for both alloys. So these are the powders that were provided to us by Admix, relatively spherical. You see the size distribution, typical for LPBF. Here, this D50, here the microns are missing, but D50 is about 30 microns, so typical size range. This is the Renishaw AM400 LPBF machine that is available at IMDEA Materials. It's a single laser, it's a pulse laser, and we work for this process optimization with this reduced build volume platform. So this is only a few centimeters, like 5 by 7 centimeters, the size of the build platform. And to start, we make just cubes, simple geometry specimens, and the side of these cubes is about 10 millimeters. So like I said before, we use a simple scanning strategy, meander, and we fix also the layer thickness and the hatch distance, so the distance between two laser passes. These two are going to be fixed for the entire presentation. So we wanted to first analyze what is the processability window using meander scanning strategy for these commercial alloys, and I'll show you the results for Cuamet. What we did vary was the scanning speed and the laser power. And all these green dots here, they represent the parameter combinations that we tried. And as you can see in the slide, I have divided this processing space in two different regions. So all these orange regions that corresponds to laser powers that were relatively high or higher than 70 watts, this was impossible to fabricate and to retain the shape of the cubes within that domain. You can see that there is delamination, excessive melting. It was impossible. So this was like a forbidden region under these conditions. We could print actual cubes in this low power region here. So what I'm going to show you now is within this small window, what can we get in terms of density and in terms of amorphous fraction, and what structure are we fabricating? Because of course we want to optimize both. We want to simultaneously get a dense material and a fully amorphous material. So let's see how far we can get there. This is color map. I'm representing just the density. So within this small processing window, no, here we have the scan speed, here we have the power, and you see the density varies from like 65 to close to 95. Here we have two optical micros. This is just cross sections parallel to the build direction, which is the perpendicular here of two cubes. So even under the best conditions, you see that the quality is not very good, and there's all these cracks, very fine cracks that are parallel to the build direction. So this is not looking very good in terms of density. Let us see what happens with the phase distribution, with the amorphous fraction. So here I just put all this X-ray diffraction together. We first got a qualitative view of the phase distribution by X-ray diffraction. The only important thing here to look at is the first one in the bottom. This corresponds to a melt span ribbon of the same composition, Quamet 6B2. We know that by melt spinning, we can produce a fully amorphous material. And the signature of this fully amorphous material is this very white halo here at 45 degrees. But if you look up, no matter, and all these KS samples, these are cubes manufactured within all this window, different processing conditions, but for all of them, we do have a bit of a white peak here, but also there is clearly a superposition of this sharp crystalline peak. So under no matter what processing parameters we use, even in the region where we can retain the shape, we are making a composite, an amorphous crystalline composite. Let us be a little bit more quantitative. By X-ray, we cannot distinguish exactly what is the structure of this phase. It could be, it's an iron silicon phase, but we don't know if it's or solid solution disorder. We can do that later by other methods. And there are also some minor fraction of borides. With the help of the team in Saarland, we calculated or we measured the amorphous fraction by differential scanning calorimetry. And this is what I show in this color map here. So again, the same processing window, scan speed, power. And the first bad news is that the maximum amorphous fraction we can get is 48%. This is very, very far from our target, which was 100%. And then here, this arrow just marks the direction within the processing space that we are exploring of increase of the amorphous fraction. So amorphous fraction increases with higher scanning speed and lower power. And I'm putting here next to this graph what I showed you earlier regarding the density. Within the same processability window, this is the density map, and the arrow indicates the direction in which the density increases. So this is the second bad news here, because these are two variables we want to optimize simultaneously, the density and the amorphous fraction. But what we are seeing is that these two variables, these two properties, they just vary in opposite ways within with our processing parameters. So this is what we call the density amorphous fraction paradox. And it looks like using simple scanning strategies, and these commercial alloys is not possible to overcome this paradox. This is just another slide. This is very similar to the previous one. This is just to show you that in the other commercial alloy that we were studying, this FineMet, that has a slightly different composition with niobium, boron, and copper, but we obtained and we measured exactly similar story. So it could only be processed and with retaining the shape in this very narrow, low power region. And if we plot within this region the density and the amorphous fraction, with respect to scan speed and laser power, again, we obtain this, inverse or opposite variation of these two variables. And again, also the maximum amorphous fractions that we could get were about 50%. So this is clearly a problem that we need to solve somehow. And this is, we are here maybe 1 year and a half already into the project, and we are faced with an interesting problem to solve. But before I show you how we went about that, I want to show a little bit how are these composites, no? These amorphous crystalline microstructures that we are creating. And they all look similar within that processing window. So I'm going to show one representative image, and we are going to increase in magnification along the different slides. So this is just as a first view, optical microscopy for this Cuamet 6v2. Here you have the processing conditions. And this is a surface that was polished and etched to reveal the crystalline region. So all these darker brownish regions are the crystalline regions. You see that it's really a composite. And if you look at the top layer here, you see very clearly this is a cross-section. No, you see a cross-section of the laser tracks. And you see that the brown regions, they are located mostly at the periphery in the heat-affected zone, no, surrounding the melt pools. So here also we can see very clearly also these cracks that I was telling you about, very fine cracks. It is true that even with these cracks, the material can be machined, it can be cut. So it's not that it's mechanically unstable, but of course it's not desirable to have that. At least not, at the very least, we want to control crack formation, not just have it, without any control. Let us zoom a bit more in this microstructure. So we used EBSD to look at these heat-affected zones, and you can see grains are mostly, well, this is an inverse pole figure map showing the orientation of the build direction. And grains are equiaxed, randomly oriented. The maximum sizes are closed in the vicinity of the melt pool, is around a couple of microns, and then they decrease in size as we go far away from this bottom of melt pools. And then on the right is a phase map of the same area. So again, most of it is red, which corresponds to this iron silicon phase, which also EBSD cannot distinguish. We can do that by TM later. And we have a minor fraction in green here in these regions of borides. Finally, if we keep zooming in, we can again analyze one of these heat-affected zones here by TM. You can see here better the morphology of the crystallites. By diffraction, we can now determine that these are ordered iron 3 silicon structures. And if we look inside one of the melt pools, then what we see is mostly an amorphous phase, as you can see here in these patterns, and then some scattered nanocrystals. So this is how this composite looks like. But let us, to finalize this first part of the talk, let us see how are we doing in terms of magnetic properties, because ultimately this is what we want. So I am going to show here these were measured by our colleagues in Italy at room temperature, using the vibrating sample magnetometer technique. Here you see the hysteresis loop, and from there we measure the coercivity. This plot represents coercivity versus the amorphous fraction. So as I showed before, and this in blue, these are the measurements corresponding to all the cubes that we manufacture within our processability window, this small narrow window. And as I said before, the amorphous fraction is not even 50%, and the coercive field is higher than 2,500 amperes per meter. And to put things in perspective, what we want is to get here, to this red circle, which is the coercive field of the amorphous, the meltspan ribbon, which is about 10, 13 amperes per meter. So we are now, at this point, still orders of magnitude away. We are learning, these relationships, but we are very far from the target. Okay, so what did we do next to try to improve this, not to break or to overcome this density amorphous fraction paradox, to try to increase the fraction of amorphous phase that we have? We thought, okay, we are going to design a scanning strategy that is a bit more complex, but that can help us to do this by the introduction of what we call time delays. Let me show you what we mean by time delays. So we call them T-off, and this off is because we shut down the laser, but I'll show you how. So this is just a schematic. This would be on the left, a typical meander scan path, the laser going back and forth. In colors, we are representing here heat accumulation. So of course, in the corners, the laser path is smaller, so there is higher heat accumulation. And if the delay times means that when the laser comes to the end of one of these tracks, we shut off the laser for some time, Then we turn it on again, and then the laser comes back. And then we switch it off, and so on. So this is switch off time after each track. So if we increase the time delay, in theory, the idea is that we allow for some time for the layer to cool down and to accumulate less heat. And hopefully, this was our hope, that this can serve us for the purpose and to solve the challenge that we have. So let me show you how and to what extent this was successful. Again, I come back to the same processability window that I was showing you before. Just as a reminder, with the simple meander scanning strategy, this blue region was the only accessible region. And now we used another system that we have. This is a Renishaw 500Q. Also pulse laser. This is multi-laser, but it allows for more flexibility of when manipulating the laser beam. So we could introduce time delays with this. And what we did is, let us see whether the introduction of these time delays allows us to access this orange region that was forbidden. Because of course, if we've used higher laser powers, it's well known that we very likely will have better density, but we need to be able to really work here. So we chose 4 conditions within this before or up to now forbidden region. And this is what I call these groups, A, B, C, D. A, red, is the highest energy, volumetric energy density. D, which is the dark blue, is the lowest volumetric energy density. And we applied different time delays to all these 4 groups, ranging from 1 to 300 milliseconds. So let us see what happens. First, let's analyze briefly the printability. And I'm showing you here one example. This is some conditions within group A. These were the highest energy conditions. And the first row is without time delays. This 1 millisecond is the default value. So this is without time delays, and here with a time delay of 300 milliseconds. So you already can see that was what was before a forbidden region that wouldn't allow even us to just print the cube itself. Now we can process a cube, so this was already good news. But let us see what we have inside. And here these are just 2 emission maps measured by a built-in photodiode in the chamber. This is infrared emission. And this corresponds to layers 46 and 66 in both samples. So you see, of course, that with the introduction of the time delays, there is less heat, less emission, which was the goal. But let us see whether this serves our purpose. This is what's coming next. So here I show you the density. We can see first in this graph the density versus the time delay versus this T off for the different groups. So if you look at the orange and then light blue regions, it looks like, yes, if we introduce time delays, the density increases. For group A, red, at least it doesn't decrease much, and that you can see here in the micrographs. This group B and C. These are 2, second and third row, and this is left column without time delays, right column is with time delay. You see that even qualitatively we can see an increase in the density. Doesn't work for group D because we are already in very low energy conditions. So if we, on top of that, let the layer cool down, basically we create more. We are in the lack of fusion region and we create more defects. But for some conditions, it seems the introduction of time delays not only doesn't hurt the density, but it can even allow a higher density. Let us see how we are doing in terms of amorphous fraction. This is key for our study, and this is what this plot shows. Amorphous fraction versus the time delay. So for all the groups, again, with the same color coding. So what we can see is already a time delay of 50 milliseconds leads to an increase under all conditions of the amorphous fraction. So this was very good news. After that, if we keep increasing the time delay, then the amorphous fraction increases, but at a lower pace. But this was good news. The next question was, before we go to see the density versus amorphous fraction paradox in these conditions, why is that? Why introducing these time delays allows us to get a better amorphous fraction, to crystallize, to lower crystallization during processing. And for that, we worked with the Professor Adrián Bocardo from the Rey Juan Carlos University here in Madrid, we did some experiments. He matched with some modeling results. This is what I'll show you in the next 2 slides. So what we did was, okay, let's go back to basics. Let us choose some conditions within group A, which are here. And then let us take an amorphous substrate and just print one single laser track. And these are EBSD band contrast maps. So here black is amorphous, and these gray tones, they are the crystalline region. So this is a cross-section. The scanning direction goes like inside the screen. So this is a cross-section of this first pass of the laser. And then what we did was to melt a second pass, neighboring pass, with different time delays. One, the default value, this is here, then here 50, and then 300. That's what you can see here. So, of course, if we don't use any time delay, the default value, this is the second melt pool. And you see what was before amorphous, what was just after the first pass was amorphous phase, it becomes, it crystallizes. No, there is the vitrification of the previously deposited amorphous phase, and all this region here, they are crystallized that form during in the heat affected zone of the second pass. What happens now if we increase the time delay? Well, you see that the width of this vitrification region decreases, especially when we go from 1 to 50 milliseconds, and it decreases slightly further when we increase the time delay to 300 milliseconds. So this is the idea, and this is why we are seeing this increase in amorphous fraction with time delay. But then the Professor Adrian Bocardo carried out some simulations for us to allow us to further understand what was going on. So he used this thermometallurgical finite element modeling. Also, he modeled two passes. And here are the two passes. B, well, this first graph here, this is a cross-section of the first track. And then this below here, we have a cross-section of track 2. And this yellow star, this is the control point. Here is where the model allowed to track the temperature evolution. So this is what we are showing here in this graph to the right. And we did that for the 3 time delays that we are investigating. So the default value, 50 milliseconds in black and 300 milliseconds in red. So let us see the differences. Well, the first part is the same of course, for the three cases. So there is a first peak here, because these two peaks are very close together. We enlarged them here, we zoomed in a bit. So when we don't introduce time delays, the second peak is already here. And the T0, that means the temperature of the control point when the second laser pass comes, is around 242 Celsius. And then if we go to the other extreme, with a time delay of 300 milliseconds, this T0 goes down to 41 degrees C. So, of course, the introduction of time delays allows the sample to cool down, and then in the heat-affected zone, the material there spends less time at high temperature, so there is less chance or less likelihood of crystallization. And this is why, time delays help to increase the amorphous phase. But then let's go back and let us see how we are doing in terms of this density amorphous fraction paradox that we wanted to overcome. And here we have some interesting data. So this is density versus amorphous fraction. And you see, for example, for group B, that we are able to reverse this trend. So in this case, both the density and the amorphous fraction, when using time delays, we can make them both vary, in the same way, in the same direction with our processing parameters. In these two other conditions, light blue, group C, group A, we can increase the amorphous fraction without at least losing or reducing significantly the density. So it does look like time delays help. But please, if you take a look at this data, you can see that the highest amorphous fraction that we obtained using these commercial alloys and even with the introduction of time delays was about 70%. So still we are very, very far from our target. Let us see how we are doing in terms of coercive field. This is what I'm plotting here, coercive field versus time delay. And again, the lowest values are about 1,000. And remember that we want to get to the value of the melt span ribbon, and this is 10. So we are still orders of magnitude, but still learning and getting there. For one thing here is that the variation, the coercive field varies with the amorphous fraction. The variation is more or less linear for fractions that are smaller than 50%, but after that, other factors come into play, which are maybe residual stresses, the size of the crystallites, and so on. This is something we didn't get into to decouple the influence of all these elements, but we could really report that then the variation of the amorphous, the coercive field with the amorphous fraction becomes more complex. And then I enter the last part of my talk, and this is where we have the good news finally. because I told you in the beginning that in this project we were, of course, collaborating with many groups, and the group in Saarland that are experts in glass science, they were working on alloy design. So by that time, they had already tried many, many compositions, and they came up with a family of alloys. I'm showing you here only one. I cannot still tell you the exact amounts of each component because this is being patented, but these are the elements of these new alloys. As you can see, this alloy doesn't contain any of the unwanted elements that we didn't want from the beginning in this project. And they managed to increase the glass forminability from about 100, 150 microns, which is the one of the commercial alloys, to 1 millimeter. So this was a very big improvement. And what we did next in this last part of the project was to see whether what we had learned regarding process optimization could be applied to these alloys to finally make fully amorphous components. And this is what I'll show you in this last part of my talk. This is what I'm going to call the new alloy, the new composition that was designed within the project. So the first question that we had, we come back again to the processability window that I showed you already many times. But the first question we had was like, well, if this alloy has now a much, much higher glass forminability, can we process it within this quote-unquote forbidden window and without the use of time delays? Can we do that? This is the first thing we tried. And this is what I'll show you now. So this was the first experiment. This is what we call J series, but basically we took some conditions. This is corresponding to group A in this processability window. And then we tried to manufacture cubes using increasing time delays from default to 200 milliseconds. So what we could see is that even in these alloys that have a much higher glass forminability, still we need some time delays in order to retain the shape. So we cannot work without time delay. So we fixed a time delay of 50 milliseconds, and then we explored the processability window. This is what we call the S series. And we varied the power within this large power region, 100 to 180 scan speed. You can see it here. And this is the density. So the good news were starting to come, because now we see that over a relatively wide processability window, the density bar is already higher than 90, which was quite good for these materials. Here again, you have a cross-section, optical micrograph, where we still, I don't know if you can see it well, but we still have these fine cracks, but the density was already much better. And then, of course, phase distribution, which is the big challenge that we have here. Again, this is a large number of samples of these new alloys manufactured within the high power region. We don't need to distinguish between them because they all look very similar. And the lower, the bottom pattern here, this corresponds to the melt-span ribbon of the same alloy. So again, with this peak white pit here at 45, so you can see now that for many conditions, we do have what looks like a X-ray amorphous material. For others, we have some small peaks, crystalline peaks, but I put here what I showed you before, this stack of patterns corresponding to the commercial alloy. So you can see that really the height and the magnitude of these peaks is much, much lower for these new alloys for a wide range of compositions here. Or sorry, a wide range of processing conditions, all this processability window that we explored. So it was looking quite good. I bring back, this is a slide that I showed you before of the Cuamet, the commercial alloy, how the composite structure looked like. We did the same with the new alloy, processed within the processability window. Within all this processability window, we polished the samples, we etched them, and look, there were, at least within this technique, within this etching method, we couldn't reveal crystalline regions. Let us zoom in a bit. But the crack problem is still there, as you can see it. But this was looking good. Then we did EBSD, and again, I bring back the EBSD map that I showed you before corresponding to the commercial alloy, and then here we get by EBSD a completely black map. So this was also looking good. And we measured by DSC the amorphous fractions, and within all this processability window, they range from 88 to close to 100%, to 99%. So this was also very good news. We measured as well, we did some TM of, this is a FIB mill lamella, which was, again, fully amorphous. And we went even to the atomic scale to see the mixing of the different elements. And the Pearson coefficient is very low, so this makes almost a fully random mixing of the elements. So this was a collaboration with Professor Parasque Vascontis in NTNU. So it looks like over a very wide processability window, we have now almost a relatively high dense with quite high amorphous fractions. How are we doing in terms of coercivity? This is the range of values that we obtain for the new alloy within all these windows. And you can see that we are now down to 40 to 70 range. So the decrease is significantly higher. Still, we are not at the level of the Melspan ribbon, which is 10, but we are getting there, and this is a future challenge. So just my last two slides, these are the remaining challenges, and mostly two things. One is that so far I have shown you I highlighted the presence of some cracks, but only using optical microscopy in 2D. So of course we cannot get a very, very accurate view of the crack structure. If we do some tomography, this is the new alloy manufactured with time delays under a condition where we get a fully amorphous structure. But when we use tomography to investigate the crack structure, this is what you see. So it's a very complex distribution of cracks. This volume comprises both the pores in blue here, and here are just the cracks. So we just segmented. But this is something that still we need to control. Cracks are not necessarily bad because they can also act as insulating agents. But of course, this is if we can control the appearance of cracks. And then the second remaining challenge is to reduce this coercive field to get really to the value of the Melspan ribbon. And for that, there's also some colleagues in the project that are already carrying out heat treatments to reduce the internal stress levels with very, very good and very promising results, which I guess will be published soon. And with that, I want to thank you all very much. These are my conclusions. The idea is this, the fact that using commercial alloys, using simple scanning strategies, it is basically not possible to get to this initial target that we have, which was to get a fully amorphous component and high density. But with the combination of alloy design and then these advanced scanning strategies, it is possible. There are some remaining challenges, of course, but we are getting, this was, I think, a step forward. And then with that, I want to thank also, these are the two PhD students in my group that are now almost about done, that have worked in this project, and of course, funding from the EU about that. And with that, I want to thank you all for your attendance. Thank you very much.
Thank you very much, Teresa. It's a very interesting presentation. I'm going to stop this recording right now.